From the beautiful studios of Way Happy, this is Mr. Meyer doing 1.4 and reminding you that second time is a charm because about 2 hours ago I did this and realized the mic was not on. So let's get back to 1.4 and I don't know, let's have deja vu for at least me. 1.4 is going to let you add, subtract, multiply, and divide two functions. It's going to let you compose two functions called composition of functions, and we're going to talk about inverses. So let's go ahead and get started now. Just a little bit of notation or what the expressions mean. Every once in a while, you will be asked to add two functions together, and that's exactly what this means in example 1. It says, will you add two functions? So there's some function f and some function g. They're both evaluated with x's in them, so can you add them together for me? So it would probably look prettier as this, function x plus function g. But I just want you to know that they will write it, or I could write it either way, and it just means add them together. It doesn't mean add an extra x in there or anything. It just means add the two functions together and leave it in terms of x. Right? Same thing here. This would be f of x minus g of x. So just subtract the two functions. Watch out. Maybe you have to distribute the negative through g of x, or maybe not. But again, this is subtracting two functions and leaving your answer in terms of x. So wherever the variable is, it should be an x. F of g, or L, sometimes they'll have a little dot in there. This is f times g, so it's f of x times g of x. You're just going to multiply those two functions together. And the last one, guess what? You're right. You're just going to divide them. And I guess I should say g of x can't be 0, because otherwise then it would look really weird. And why is all that there? Good? That's all we're talking about when we're talking about adding, subtracting, and multiplying and dividing two functions. So let's go ahead and show you how to do this, or why it would happen. And let's talk about the domains and all that, because that's usually the tricky part. So here you have two functions, f of x and g of x. What are the domains of those real quick? Well, look at f of x. It's not hitting any of our three rules, right? There's no square roots, there's no logs, there's no fractions. So this guy is definitely all real numbers, or negative infinity to infinity is his domain. The square root x plus 2, ooh, that is a little tricky. We have x plus 2 has got to be greater than or equal to 0. So x has got to be greater than or equal to negative 2. So therefore, this one's domain would be negative 2 to infinity. Again, just nice to know domains, right? Means that you shouldn't have x's ever that are smaller than negative 2. So let's go ahead and find this function. So the new function we are going to create is going to be the subtraction of the 2 up there. So I'm going to do g of x minus f of x. So g of x is x plus 2, square rooted, minus, now minus all of f of x, so I guess I'll put it in parentheses to remind myself that it's minus all of that. And what do I get? I get the square root of x plus 2 minus 6 plus x. And I really can't clean that up any. That's kind of gross, right? So there it is. That is g of x minus f of x. That is the function. So there it is. There's our new function created by combining two other functions. What about its domain? Now look at that. The domain, there's no restriction on the x. The 6 doesn't matter. But oh, right there, the x plus 2 under the radical. Its domain would be negative 2 to infinity. Interesting to see that it was the same domain as up there. And in fact, it makes sense because it was created from those two. And most of the time, you got to go with the more restrictive domain. Right? Because it has to be the domain that is more restricted, because I can't just make up numbers that would cause something bad in one of them. And there's your answer. All right, what about this next one? It looks like I'm going to have to do f of x over g of x. All right, little division. So f of x we know is 6 minus x, and g of x we know is root of x plus 2. And bam, I can't reduce that, so I'm finished. That's as quick and easy it is. So you know that wasn't so bad. So it must be the domain part that's the bad part. Well, let's look. Numerator has no problems. Ooh, denominator, right? Can't have a square root down there. It can't be negative under it. We knew that already. 2 to infinity, or negative 2 to infinity. But in this case, we can't use negative 2 either, because it would put the other restriction, which would be a 0 in a denominator, and that would be oh so bad. So we have negative 2 to infinity, but we are not going to include the negative 2 in the domain because of the fact that we don't want a 0 in the denominator. There you go. That's how you do some quick compositions or, adding or subtracting. But what about the nasty composition, the open circle composition? See how it looks a little different? Sometimes I call it fog, right? What does fog actually mean? Or if it's the other way around, g of f of x, goth. It means that you're going to plug one function into another, right? In fact, up there in the notes, I think there was like a g of x or something like that. G of x was the square root of x plus 2. And that's really the composition of two functions. One function that adds 2 to the x, and then one function that square roots it. So that really was already the composition of two functions. Wow, isn't that kind of neat? So now we're going to do it with even more complex stuff. So the big catch here is pay attention to the order of the g of f of x or the f of g of x. And to save myself that frustration, what I do is a little bit of substitution. This is g of f of x. So this is g of, and I'm going to substitute what f of x is. It's 1 minus x squared. I'm going to substitute that in. So what I'm really going to do is take equation g and evaluate it for 1 minus x squared. Now, first, that might look spooky, but remember, you've done this. We've asked you before, what's g of 2? And that means go to equation 2 and go to equation g and plug a 2 in. You'd get root 2. I could say what's g of 5? And that means go to equation g and plug a 5 in. I could say what's g of m, right? So that would be go to equation g and plug an m in where the variable is. So it wouldn't scare you any. So now this is just saying go to equation g and plug a y minus x squared in where the variable is. So that would be the root of 1 minus x squared. There, you've done it. You've done the composition of two functions. Now, be careful. This is where you'll get tricked. That doesn't simplify, right? I know we know the square root of 1. I know we know the square root of x squared. But because of the minus holding that all together, that's one whole number, we cannot just rip it apart. We could factor it. It's a difference of squares. We could have 1 plus x, 1 minus x, but still that's not going to help me under the square root. So I'm kind of done, right? So there it is. That is our answer to the composition of g of f of x, right? Now the mean part, what's the domain? Well, domain, same old rules, right? Is that you have the 1 minus x squared has to be positive, or 0. So 1 minus x squared has to be greater than or equal to 0, and I need to solve that. Now inequalities are gross when you can't just solve them real quick. I could move the x squared over and then I'm stuck, right? So I need to find another way, and here's a way, or one of the many ways I could do it. We said it was the difference of squares, so 1 minus x, 1 plus x is greater than or equal to 0. Now that I've factored it, I can put it on a number line, and I can say, all right, let's solve this for when x is 0, right? So I'd move it over and say x is 1. So at 1, I fill it in because when x is 1, I get 0, and I'm okay to have zeros because of the equal to part. And then I solve this one, what happens to be when x is negative 1. So I'm going to fill that in. But what about everybody else on the number line? So I know negative 1 and 1 work, but what about everyone else? Well, the cool thing is when you factored it, you've created critical points, and then you just test everything else. So I'm going to test to the left of this critical point. So I'll test something like negative 2, negative 3, whatever. Let's do negative 5. When we plug in a negative 5, we get 6, and we get negative 4. And when we multiply that together, we get a negative number, which is not greater than 0. So these do not work. Then I'll test in between here. So let's test 0. We get 0. We get 1 times 1, which is 1. That is greater than 0. So 0 works, means everybody in between the two critical points works. And then we test somebody bigger than 1, like let's say 10, because that's over this third region that I need to check. 10 would give me 1 minus 10 is negative 9, and 1 plus 10 is 11, so negative 99, which is not greater than 0, so it doesn't work, so none of these work. So in fact, the only things that work are all the numbers from negative 1 to 1, so the domain goes from negative 1 to 1. That is the domain of that function. It is a very restricted function, right? It can only work for that section. All right, what about fog? Would it be the same answer if I did it the other way? Well, let's find out. you would do f of g of x. So g of x we know is square root of x. And so I'm going to plug that into f. So it's going to be 1 minus, now I'm going to take the x out and put root x in there. And now with that squared, I can now simplify that. Ooh, the square and the square root cancel, you get 1 minus x. Woo! And you're like, there is the fog. Notice it's different than the Goff, so order does matter when you do fog and Goff problems, so be super careful about your work. The other thing you want to notice too here is this one has really, this is just a line. It has no restriction on the domain. So you would think your domain is all real numbers, but you would be wrong. The reason being is because it was created from this function, right? And this function still holds true. This thing still exists. This is still the function g. And we know that g cannot be negative, right? It has to be from 0 to infinity. So this guy actually carries that restriction along, and he can only go from 0 to infinity. So that is his domain. Crazy, right? All right, let me ask you a couple questions, and then we'll go on and do inverses. Inverses are great. They help us solve lots of things, right? If you're trying to find an x, if you have x squared equals 9 and you want to solve it, you actually use an inverse. Square rooting is the inverse of squaring, right? When you have 5x equals 10 and you want to divide, that's because division is the inverse of multiplication. It helps us solve things. So inverses are very important in the world of math. So let's talk about them. Inverse, what if you have a graph and you want to know if its inverse is a function? Okay, right? How would I do that? Well, I do what's called a horizontal line test. It's just like a vertical line test. A vertical line test tells me if the graph I'm looking at is a function. A horizontal line test tells me if the graph I'm looking at, if its inverse is a function. So look at this first one here, this x cubed. I know it's a function because it passes a vertical line test, but what about its inverse? Would its inverse be a function? Well, I just do a quick horizontal line test. So all I do is take this and I go, oh yeah, slide it up and down, only hits the graph once. So sweet, I know that this guy's a function, but I also know that the inverse, h's inverse, or I'll say its inverse is a function. And they said why, so I would say because it passes the horizontal line test. HLT. It passes the horizontal line test. And that's it. Right? Done. I know the inverse is a function. Now, looking over at the second one over there, I can do the same kind of thing. I can pull my little fancy arrow over and oh, it's hitting twice. Right? So even though this parabola is a function, its inverse is not a function. So its inverse isn't a function. It's like deja vu all over again. And that's because it fails the vertical line test, or the horizontal line test for those people paying attention. And so we're good, right? So let's talk about how you find inverses. So now that we know we can look at it and tell if the inverse is a function, what about how can I find it? So there's 3 ways. There's finding it graphically. And all that is you look at a graph, and then if you want to find the inverse, you reflect it over that diagonal y equals x line. Super hard for me to do because I'm not that visual. Other people are super visual and can do it. I'll show you one, but I'll do it after I did the math. Second way is to plot a bunch of points. That's called numerically. So you plot a bunch of points, and then you switch their x's and y's, and then you plot those points, and that will be the inverse. A lot of work though. And then algebraically says, hey, take the equation that you have and again switch the x's and y's, or what I like to say is replace all the x's with y's, replace all the y's with x's, and then go ahead from that step, make it say y equals, and that will be your inverse. So that's the way I will do example 5. So here I am on example 5, and I know that f of x means y, so it's y equals x cubed minus 1. To find the inverse, I will replace all the y's with x's, and I will replace all the x's with y's. And really, that's the inverse. You've just done the work. Now we like it to say y equals, so let's pretty it up a little bit. I'll add 1, and then I will cube root, and lo and behold, I have the inverse. And you'll notice here that if it's a function, you can write it as the inverse function looks like f to the negative 1 of x. That's how I say inverse is equal to the cube root of x plus 1. And I jump up and down. There's the inverse. Now, I said I would talk about it graphically real quick, so here it is. The original one we'll do in black. So the original one was a John Travolta graph, down 1. So I go down 1, and I make my up on the right and down on the left for John Travolta, and we're golden, right? Now reflect that over the red line, which I usually do the red line after, but I'm going to try to see if I can be visual. Reflect it over that line, right? So the way it would reflect over that line is exactly what this graph is. I'm going to cheat. This is a cube root graph, and it is shifted left 1 unit, so left 1 unit, and then it's a shooting star graph that has a tail. Now, that's probably what the visual people were saying. Yeah, it would look exactly like that. Now I see it, and I'm like, oh yeah, those are inverses. It definitely reflects over the red dashed line. And I'm like, oh, that's great. But I couldn't do it before. I always have to do it algebraically or even numerically before graphically. But there you go. That is the inverse and the graph itself on there. Now, how do you verify things are inverses? So say I give you 2 and I say, hey, are these inverses? Well, it's kind of neat. You take the function and the inverse and you do a composition, and everything should cancel out. So what will happen is you will take f and f inverse, you will do a composition like we saw a little while ago, and the only thing left should be x. That's it. Everything else should cancel. And then you should really do it the other way too. You should do the inverse. You should plug the original into the inverse, and everything should cancel out and be x. So you need 2 equations, right, to verify that something is an inverse. Now, how do you do it? Now, we're going to go up and we're going to do the one we just had. So we had f of x, which was, I think, x cubed. Was it plus 1 or was it minus 1? It was x cubed minus 1. And then we had, I was going to say g of x, but I want to call it f inverse of x. That guy was the cube root of x minus 1 or plus 1. So there they are. And now I'm going to verify that they are inverses, that all my work was true and right. And the way you do that is you first evaluate f of f inverse of x. So that would be f of the cube root of x plus 1. So go to equation x, or f, and plug this mess into where the x is. Right? So what would that be? That would be the cube root of x plus 1, and then that whole thing cubed, because that's what's happening, minus 1. Well, look what happens. The cube and the cube root cancel. That's cool. X plus 1 minus 1. And then the 1's cancel. You get x. Hey, it worked. Well, we got to do it the other way too. We got to do f inverse of f of x. But it should get us just down to x. So f inverse of x cubed minus 1. So we're going to go over to f inverse. We're going to take that x out, and we're going to put in x cubed minus 1. And then right behind it will be a plus 1. Well, good news. Look what happens. The 1's cancel. And now cube root of a cube, you're left with x. And you have just verified that our inverse was correct. That's awesome. Don't worry about the next 2. I'll do those in class. And you have a great day. Stay happy. Do your homework twice just to make me, or watch this video twice. But you know what? Mute it the second time just so you can feel what it was like. Have a great day. See you tomorrow.